Hi guys, this is Dr. G here, and in this short video we will talk about Friedel-Crafts Acylation. So in a previous video we actually discussed on Friedel-Crafts alkylation. So acylation is actually very similar to alkylation, so they are both electrophilic aromatic substitutions. So in this reaction basically what we are trying to do is we are trying to substitute one of the benzene hydrogens. We are going to substitute one of the benzene hydrogens with an electrophile, and of course in acylation the electrophile is going to be an acyl group, so you will have a carbonyl group and an R group. Okay, so basically in this Friedel-Crafts acylation we are trying to substitute a benzene hydrogen with an acyl group. So the reaction is very straightforward and similar to alkylation. So the reagent that we use in here is actually a carboxylic acid chloride. Okay, so you need to have a carboxylic acid chloride, and this carboxylic acid chloride will be selected in such a way that it will have an R group that is desired to be present in the benzene group. Okay, so depending on the R group that you select, okay, depending on the R group that you have on the carboxylic acid halide, you will get a different substituted product. And the catalyst that we used is going to be aluminium chloride, and you will use high temperatures to achieve this reaction. And then this reaction is actually a high yield reaction. Usually you will get around 90% or more yield. So this is actually a very popular reaction. And here's the reaction mechanism. So I'm not going to talk about the reaction mechanism in more detail. So I will highly recommend that you guys go ahead and watch the reaction mechanism for electrophilic aromatic substitution, and also Friedel-Crafts alkylation mechanism, because this mechanism is very similar. In this situation, in this reaction, you are going to need an electrophile. You're going to need an electrophile. So the electrophile in this reaction will be an acyl cation. Okay, so the electrophile that we have in this reaction is an acyl cation, and the carbon atom will have a positive charge which will act as the electron deficient site for this substitution reaction. So just like in any other electrophilic aromatic substitution reaction, the electron attack will happen from the benzene ring, and it will attack the electrophilic carbon. And then once the carbocation is formed, you will no longer have the aromaticity on benzene. Okay, so aromaticity is an extremely stable structure. Aromatic compounds are very stable, but because of the addition of this electrophile into the ring, it will lose aromaticity. So this carbocation is highly unstable. So in order to reach some, in order to obtain some stability, this carbocation can show resonance structures. Okay, so you might want to see if you could draw a couple of other resonance structures for this particular carbocation. Okay, but of course achieving the aromaticity is the most important thing. So in order to achieve aromaticity of benzene, you will use the 2 electrons on the carbon hydrogen bond that has the new acyl group, and then those 2 electrons will be used to regain the benzene aromaticity, and also this reaction will regenerate your catalyst. All right, so this is the general mechanism. I'm not going to show you how it happens in more detail, because by now you should be very familiar with it. All right, so as an example, let's say you want to synthesize a compound or an acyl compound like this. Okay, so let's say you have a benzene attached to a carbonyl, and then maybe something like this. Okay, what type of a reagent will you need for this reaction? See if you could pause the video and come up with a reagent or carboxylic acid chloride for this reaction. Okay, so of course you will start with benzene. Okay, you will start with benzene. There is nothing attached to benzene, of course, in the beginning. And then this is your product. Okay, so the only difference between product and the carboxylic acid halide is that instead of benzene you will have a halogen. Okay, that is the only difference. So instead of benzene you are going to have a halogen, or chlorine in this case. All right, so instead of benzene, put a chlorine in there, and you will also need aluminium chloride and heat. So this will get you your desired acylated benzene. All right, so it's a very straightforward reaction. So you should be able to draw the product using appropriate reagents necessary. And all you need to remember is that whatever the R group that you will select, will be present in your product. Okay, will be present in your product. All right, so with that, I'm going to actually go to your lecture note, because there is a worked example that I want to show you, and I want to see if you could complete that worked example at this level. Okay, so let's jump back to your lecture note and see if you could do this worked example. So in this worked example, I want you to identify the carboxylic acid halide that might be used in the Friedel-Crafts acylation reaction to prepare the following compound. Okay, so I want you to pause the video and then see if you could get this answer. Okay, so all you need to do is highlight a benzene that is directly attached to the carbonyl, and then replace that benzene with a chlorine. And then everything else is exactly the same. So this is your reagent. This is your carboxylic acid halide, and you will react it with benzene in the presence of AlCl3 to obtain this particular compound. All right, so here is your detailed answer. You might want to pause the video and write down the details if you have to. Okay, but this is how you do it. One of the most important things about this Friedel-Crafts acylation is that this acylation is actually a good substitute for Friedel-Crafts alkylation. So this Friedel-Crafts acylation is an excellent substitute for Friedel-Crafts alkylation, primarily because of certain reasons. So if you remember alkylation, Friedel-Crafts alkylation, it had some severe limitations. One of the most important limitations is that sometimes when you are using an alkyl halide to generate alkylated products, alkylated benzenes, these carbocations that were formed by alkyl halides could rearrange. Okay, so the product that you get might not be similar, or might not what you expect in the original reaction. Okay, as an example, let's take a look at this one. Okay, so in this alkylation reaction, I want you to attach a propyl group. Into benzene. So what you will do is that you will take the propyl group, right, 3 carbon alkyl group, attach it to a chlorine, and then use AlCl3, hoping to get the alkylated product, right? But in reality, what happens is that this particular compound will not be the major product. Instead, this will be your minor product. The major product is actually an isopropyl group attached to benzene. And you know why. The main reason for this is that when you use this alkyl halide, the carbocation it forms is a primary carbocation. Which is not very stable. which is not very stable. Instead, if you can form a secondary carbocation by the hydride shift, if you can form a secondary carbocation by the hydride shift, the secondary carbocation will be more stable. Okay, secondary carbocation will be more stable. So therefore, there will be a rearrangement in the intermediate carbocation or the electrophilic carbocation, and therefore the product that you will get, the major product that you will get will have a different R group or alkyl group as compared to the R group that you were expecting. Okay, so the major product will be totally different. The major product will be different. So that is because of the rearrangement of intermediate carbocation ions. Carbocations. The other limitation that is associated with Friedel-Crafts acylation is polyalkylation. Okay, it is polyalkylation. So I think I mentioned this in more detail in a previous video when we talk about Friedel-Crafts acylation. So in summary, what happens in this polyalkylation is that, let's say you're hoping to get an alkylated benzene using a certain alkyl halide. Okay, let's say you are using this alkyl halide hoping to get an alkylated benzene. Let's say this is the one that you're hoping to get. But once you have this alkylated benzene, this alkyl group can actually activate the benzene ring, and this activation will result in polyalkylations. This activation will result in polyalkylation. So rather than getting one alkyl group on benzene, you might get two alkyl groups. So this is also a huge problem. So because of these limitations, sometimes it is more beneficial to use acylation over alkylation, and let me show you why. Okay, let me show you why. So let's try to synthesize the same alkylated benzene. Okay, so let's try to synthesize this same exact alkylated benzene. So you have a propyl group attached to benzene. So if you go through the acylation pathway, you need to have a three carbon chain. Okay, so you are using this carboxylic acid halide, and then this is your acylated product. But once you obtain this acylated benzene, what you do is you will reduce this acylated benzene to achieve the alkylated product. Okay, so you will reduce the carbonyl group. Into a CH2 by using a simple catalytic hydrogen reaction. Okay, so in the second step, you can easily reduce the carbonyl group into a CH2, where you will receive your desired alkylated product. So rather than using alkylation, it is more beneficial to substitute alkylation with acylation followed by reduction. Okay, so whenever you are planning on using alkylations, you might want to always worry about the limitations of alkylations, and if you feel like these limitations could impact the alkylated product, the better way to do this is actually to go through acylation followed by reduction. This will basically give you your desired alkylated benzene without any of the limitations such as rearrangement or polyalkylation. With that, I'm going to conclude this video, but please let me know if you have any questions. Okay, you guys have a good one. Take care.